Welcome back. So we looked there in the last video with the way we can have a normal curve that's kind of close to normal, in which case we might as well just swallow the fact that we're going to be a little bit off and deal with that. But like I said, when the error or when the skewness or when it starts to be significantly far removed from a normal curve, what we will do in this class at least is just acknowledge that. Just be open and honest to the fact that our curve, whatever it is, isn't exactly normal. It isn't perfectly normal, but it's going to still tell us some information. So, what I have here is some pre prepared examples for skewness. Now, skewness is where you've got a normal ish curve, right? So the dashed line here is a perfect normal distribution. And the red shape here is my skewed normal distribution. It is skewed to the right, so called because it looks like I've just grabbed it with my palm and slid it to the right a little bit. It's also called right-tailed because if you look from the peak here, it takes longer to reach the bottom if we go to the right than if we go to the left. So it's called right-tailed, it's called skewed to the right. It's also called positive skewed because it's biased in favor of the positive x-axis here. And so those are all different ways of talking about skewness. This, I don't anticipate, will be the last time we talk about it, but if it is, well, you at least know what I'm talking about. Now, that said, the issue with skewed data is it's still normal-ish. You can still find a mean. You can still find a standard deviation, which means you can still make z-scores. You can still look it up on the normal z-tables, and you'll still get numbers. But I want you to notice something. To the left here, this is the actual curve right here. This is the normal distribution that we're assuming we have, but we don't actually have. So if we do use mean and standard deviation, our estimates are going to be too high because the z-table will give us what the dashed line represents, whereas this is what we actually have. So if you have a data set that is skewed right, meaning it's right-tailed, it's positive skewed, you're going to have results that if you assume normality will be too high. And you just have to acknowledge that. There are corrections that you can make that we're not going to cover in this class because it's pretty involved, but that is just something that we're going to acknowledge right now. That if we don't have a perfect normal distribution, we just got to talk about what we do have. Similarly, if you're skewed to the left, meaning you just smush down with your palm and slide it off to the left, the whole thing is now biased in favor of the negative x-axis. The left tail is longer. Those are all meaning the same thing. Note here also that if I were to try and just pretend that I had a perfectly normal distribution, being the dashed line here, my estimates from a z-table would be too low. And that's not inherently a bad thing, right? A low estimate is better than having no clue whatsoever. Better yet, improved by the fact that you are acknowledging that it's going to be too low. So really, that's all I wanted to say about this right now. I'm not going to get into normal quantile plots or anything like that. If you do want to look into that, you certainly can. But honestly, for this class, for this course, we're just better understanding where our normal curves start to fall off, where they start to be less and less accurate. And that's going to be good enough. Just something to keep in mind as we work through this semester. Yeah, not everything's perfectly normal, but a lot of things are decently normal, approximately normal. And that's good. I think that's a good stopping place for this section. Like I said, no homework assignments for this one. It's just something to think about as we go forward. So in the next videos, we will get into the next section where there will be some homework, there will be some number crunching. So I will see you then.